Hey everyone, today I'm going to be presenting the multi-target compilation stack for GeneSys. But before we get started, I just want to say a little bit about myself. My name is Christopher Priebe. I am a second-year PhD student here at UC San Diego in computer science and engineering. But broadly, my research interests are in compilers and computer architecture. More specifically, I work on compilers for cross-domain applications. An example of a cross-domain application would be an autonomous driving software that requires signal processing to convert the raw data from like sensors into some sort of data that can be consumed by another application, maybe then machine learning to make some sort of predictions, and then the control theory to actually provide the means to do the updates. So those three domains would be in a cross-domain application. I also work on multi-target compilation, which entails compilers that can compile for various domain-specific accelerators. For example, I can compile to our own accelerator or a different kind of accelerator. And then finally, I also work on machine learning-based compiler optimizations for both cross-domain compilation and multi-target compilation. If you are interested in checking out my work or you want to get in contact with me, the QR code in the bottom right there, right down there, can take you to my website. It has all of the details, including my contact information. Also, I want to quickly thank the people who have made this compiler possible. First and foremost, there on the left, Dr. Sean Kinzer. He is the primary author of the compilation stack that I'm going to present, and he was also a great mentor during my first year as a PhD student. I also want to thank Rohan Hanyang and Dr. Sarush Gujrati for helping to verify the compiler throughout its implementation. So moving on to the actual content. So on the left here, we have sort of the typical 5-stage pipeline model for a general purpose processor. And CPUs, general purpose processors, are based on the von Neumann model of computing, which involves sequential fine-grained instruction execution. However, when we look at rapidly emerging DNN accelerators, they tend to use other models of computing. For example, systolic, as in the case of Google's TPU, or data flow in the case of Microsoft's Brainwave. These accelerators typically consist of one or more arrays of processing elements. You can see on the figure a square array of processing elements. And you can see on the figure as well that these processing elements are typically connected to each other and some sort of interconnect with a memory hierarchy that is completely software managed. So as you can tell, fundamentally, these are completely different. And therefore, we need a new abstraction for compilation. Furthermore, existing frameworks rely on an LLVM backend. As you can see in the figure, if we're trying to compile to a CPU or maybe to a GPU through PTX, we would typically just go through LLVM. It's a very mature infrastructure. However, if we're trying to compile to some new accelerator, this sort of interface doesn't exist anymore. And so therefore, we don't have the ability to compile to just any arbitrary accelerator. So given this gap in our backend compilation support for different accelerators, we need to identify what makes this task difficult so we can solve it. There are 4 main challenges that need to be addressed. Specifically, we need to be adaptable to different compute models. We need to be able to handle software-controlled on-chip storage. We need to be able to keep track of data movement to different resources in the accelerator. And we need to be able to efficiently map operations from high-level algorithmic representations onto the specific hardware components that can most efficiently carry out those operations. So I'm going to take a little bit of time here to delve into these challenges a little bit more, starting with the first one, the diverse compute models. If we think about a typical CPU, we're going to be dealing with only fine-grained instruction execution, maybe basic arithmetic operations or basic logical operations. However, when we're looking at a DNN accelerator like the one on the right, The example here is a systolic array, and we can do an entire matrix multiplication in one instruction with a systolic array. So now, instead of just easily being able to put everything into the finest granularity, we need to be able to target these coarser compute granularities if we want to fully leverage the abilities of these domain-specific accelerators. When we're dealing with general purpose processors, while we are going to be manually loading and storing data from our main memory into our register file, the intermediate memory hierarchy, specifically I'm talking about the cache hierarchy, are completely hardware managed, which relieves a burden off the compiler. However, when we're dealing with domain-specific accelerators, there could be a large memory hierarchy of scratch pads that are completely software managed. So we have to keep track of the data that's on there, and we need to do validation to make sure that the data fits. So next, sort of in line with what we were just discussing about having to keep track of data on our on-chip scratch pads, when we're looking at a general purpose processor, data from the register file is moved automatically to the compute units, in this case, just the ALU. However, when we're looking at a domain-specific accelerator, we can't necessarily guarantee that just loading onto the scratch pad is going to make this available to the compute unit. So now our data movement is explicitly managed by software. So therefore, we need a new hardware-software abstraction to address these challenges. And we have devised the architecture covenant graph to model these microarchitecture features and enable reusable compilation across different domain-specific architectures. So this challenge of creating an architecture abstraction requires us to capture details of the microarchitecture that are relevant to compilation. And we can leave out any details that we don't need for compilation, but might be important for the architecture design. For example, like the controller, this finite state machine controller is obviously important to the architecture, but we don't need this when we're doing compilation. And this figure highlights this well. We have some components that are unused here, like the controller, but we do care about our memory hierarchy, how that data is moved, and our compute units. So we modeled these components specifically in a graph. And so here the vertices of our graph are memories and the compute units, and the edges of the graph are the interconnects. So this gives us a sort of topology of our architecture in graph form. And additionally, we need the information about these vertices and edges. So we need information about how big the memory is. We need information about what operations the compute units can do. And we can store that information in the vertices and the edges as attributes. I'm going to talk a little bit about these, here in just a second. So like I was saying, we want to be able to capture the different compute capabilities of the compute nodes in our architecture. So here we might store that our scalar unit can do some addition on this data type, but our matrix unit can do a full matrix multiplication. And this information can be used by the compiler to efficiently map high-level operations to the specific hardware components that will most efficiently execute them. Next, when we're dealing with on-chip storage, we have to check if the data can fit on there. So we have the attributes like the data width, the number of banks in our memory, the depth of the memory, and this will tell us how big the memory is, so we can efficiently allocate memory and keep track of the data in our storage. And finally, when we're dealing with the interconnects as the edges, we need to do the bandwidth so we know how much data we can send across each interconnect at one time. So now we've discussed the architecture covenant graph, and this gives us a great way to represent the topology of our architecture. However, it doesn't tell us how we actually want to execute our operations on our architecture. And for this, we have devised codelets. Codelets are a low-level programming abstraction, and they specifically use details from the architecture covenant graph, like the memories, the interconnects, and the compute nodes, to represent how we can do these operations, thereby forming a schedule for our high-level algorithms on our architecture. Here I have an example codelet for ArrayLu on a 4-dimensional input. This codelet is represented as a Python function that takes in the architecture covenant graph and outputs a template that will be instantiated during compilation. Now, I'm going to go through each part of this codelet so that we can understand how they work. So the first step in a codelet is defining dummy operands for the dimensions of the input and output tensor. This lets us reuse our codelets across different networks that have different data shapes coming in. So here we see a dummy operand created for each of the 4 input dimensions that link the input shape of the node taken from the Onyx file to these dimensions that we can use throughout the codelet. Then we use dummy operands to define the input and output tensors for the ReLU. So next we need to define our loops that we're going to iterate over each dimension of the input and output tensor. Then we'll define the body of our codelet, which is where we are going to do our transfers from DRAM to our on-chip scratch pads. We'll actually do the computation, and then we'll store again. And finally, we will add some compilation constraints that the compiler can use to ensure that our output code is valid. Sweet. So we've gone over the background behind our compiler, which are the architecture covenant graph and the codelets. Now we can go over the overall compilation flow, which leverages the architecture covenant graph and the codelets to enable multi-target compilation. So the first step in compilation is instantiating the codelets. Our compiler takes an ONNX representation of the neural network as input. ONNX stands for Open Neural Network Exchange, and we use ONNX because it's highly interoperable between popular deep learning frameworks such as PyTorch and TensorFlow. So given this ONNX graph as our input, the compiler parses the computation graph. It sequences the nodes in topological order, and then it maps the operations of each node in the computation graph to their corresponding codelet implementations. During this mapping, we fill in compile time parameters such as tensor shapes, stride, and padding. Additionally, if operator fusion is enabled, which is one of the front-end optimizations that we support, valid fusions are performed and mapped to their corresponding fused codelets. The next step in compilation is to optimize the instantiated codelets. This involves processes such as tiling or memory allocation. These optimizations are done with the architecture covenant graph for the target architecture as context. Using this information, we can do target-specific optimization, and therefore we can do efficient multi-target compilation. As an example, we can optimize the tiling for an input or weight tensor to specifically cater to the target architecture using our architecture covenant graph. I'm now going to give a short example of how tiling might work. So here we have an example image on the left. We got the height and the width of the image as normal, and the channels, for example, in an RGB image, there would be 3 channels, red, green, and blue. So there are many, many different ways we can tile this to specifically cater to our memory hierarchy. For example, it might be more beneficial just to tile the height and width dimension and not to tile the channel dimension. This is going to be very useful if we're doing a reduction because we don't have to do any sort of partial sums, but then we also might have a larger tensor. However, we could also tile the height, width, and channel dimension, which is fine to do if you're maybe doing an element-wise computation. If you're doing a reduction, you might have to do to load partial sums again. But here, now we have smaller tiles that we can put. So overall, one of these is not necessarily better than the other, but the idea is that we can enable both of these things. So we're very flexible to whatever is going to be best given your architecture covenant graph. Now, the final step in compilation is code generation. The architecture covenant graph here contains instruction templates that map operations in the codelets to groups of assembly instructions. So using this, now we can automatically generate accelerator binaries using the architecture covenant graph. So if you want to target a different architecture, all you need to do is define a new architecture covenant graph with these instruction templates embedded, and then you get automatic instruction generation. Additionally, our compiler also implements a PyTorch model of the various layers in the neural network, and it uses this to generate a golden output for your model. This can be used for hardware verification, for instance. And with that, that is the end of this segment of the video. If you have any questions, feel free to reach out to me. Continuing in this video series, we're going to be doing some interactive examples of compiling a ResNet and a BERT model. So stay tuned. Thanks for watching.